the Chesapeake Consortium, which is organized for the DOT proposal. And the purpose of this is to build 10 prototype vehicles and also arrive at a more production-worthy design. And he'll probably also mention the Department of Energy hybrid vehicle program. Okay, here's some highlights of the Westinghouse electric vehicle propulsion system. And there's a few mistakes on here that I told Barbara about, that 0 to 60 is really 12.5 seconds. And the second line is 275 horsepower. It should read regenerative braking absorbs up to 275 horsepower. High efficiency system pertaining to the induction motor, smooth power over the range, 100,000 mile without maintenance, acoustically quiet, electrically quiet. Okay, the purpose of this slide is to show the progression of cost over time and what makes up the cost and how the material cost and labor cost will come down to the target value over that period of time. So this is the first time I've seen this slide too. So if you see anything on there that needs to be changed, okay, I think in the meantime, though, we can make the change to that other slide. Okay, Ted will give me an introduction. I will give a basic overview of the Westinghouse electric vehicle propulsion system development. And these are the topics that I will cover. Some basic vehicle terminology, modes of operation of the electric vehicle, some system power and performance numbers, and system energy consumption information. I'll also give some comparisons between electric vehicles and standard internal combustion engine vehicles with some surprising road test results. Throughout the presentation, I'll refer to two test vehicles that were assembled last year. One is a Chrysler minivan. This was provided by the Chrysler Corporation. Westinghouse and Chrysler have a teaming relationship to develop electric vehicles. The other is a Dodge Dakota pickup truck, which we bought new and placed the same size motor and controller in it that's in the van. This vehicle weighs about 1,500 pounds less. This is a simplified block diagram of an electric vehicle propulsion system. In this diagram, energy flows from left to right, from the battery to the motor controller, which provides variable frequency AC to drive the motor. The motor transmits mechanical power through a single-speed gear drive to the wheels of the vehicle. There are also some other components shown here, a DC to DC converter that provides 12 volts DC for the automotive loads, and an onboard battery charger, which charges the battery from a utility grid. This is what the hardware looks like mounted in the van. In the upper left corner, you can see the battery trays mounted underneath the vehicle. These are nickel iron battery packs with 30 cells underneath and another 6 in the cargo area. In the middle, under the hood, you can see the motor controller. It's liquid cooled, is a little over one cubic foot, and is limited to 500 amps DC, both charging and discharging the battery. The motor can be seen in the upper left. There's a flange on the motor which was designed to match an automotive front-wheel drive transaxle, which is shown in the lower right corner. This is looking underneath the vehicle, and the motor can be seen connected to the transaxle. This was modified by Chrysler so that it only has one gear ratio, one speed, so that there's no clutch and no gear shifts required. I'll probably omit this slide because in Carlo's presentation he'll have a similar slide that describes motor horsepower and torque. There are three modes of operation: the driving mode, where energy is taken from the battery; regenerative braking mode, where energy is returned to the battery; and battery charging from a utility grid. The propulsion system shown at the top indicates the energy traveling from the battery to the chassis, and the graph below it shows the amount of power that exists in the propulsion system at various points. At a steady speed of 55 miles an hour, the van requires about 21.5 horsepower, and this is used to overcome friction and wind resistance. The other amounts of power that are shown indicate particular system losses as we travel from the battery to the vehicle. The arrows pointing downward are system losses indicated in terms of horsepower. So at this particular mode of operation, the system is delivering about 21.5 horsepower. Now the system is capable of delivering horsepower up to 100 into the axles, and this is a family of curves showing the power levels that exist for various steady state speeds up to 105 miles an hour. 105 miles an hour is the theoretical top speed of this vehicle if 100 horsepower were delivered. The upper curve over where the battery is shows that there is considerable battery loss at these high currents. That high horsepower level is used for acceleration for anywhere from 12 to 17 seconds in these two vehicles. And after that period of acceleration, the power drops back down to about 20 horsepower to maintain a steady speed. So the energy dissipated in the battery at 100 horsepower is about 30 kilowatts. And then this drops down to less than 1 kilowatt, about 750 watts at cruising speed. During regenerative braking, the system absorbs energy from the vehicle and returns it back to the battery. The lower curve indicates the maximum power available when the system is delivering shaft horsepower to the vehicle, which is 100 horsepower. The upper curve indicates that the maximum shaft horsepower that the system can absorb is about 275 shaft horsepower. This amounts to a battery charger that can charge at a rate of 150 kilowatts for a short period of time. This is about 200 horsepower going back into the battery. The third mode of operation I mentioned was battery charging from the utility grid. And in this example, if a user purchases 50 kilowatt hours of energy, and if the overall system efficiency is about 80%, that means that he'll end up with about 40 kilowatt hours of usable energy in the battery. This energy cost amounts to about 2 cents a mile, assuming that the off-peak energy rates are about 5 cents per kilowatt hour. So the energy cost is very low. This is equivalent to $1 a gallon for gasoline and 50 miles per gallon. So the range of 110 miles actually depends on how much energy the vehicle absorbs per mile. And this can be understood by looking at some basic relationships. One basic idea is that force times distance equals energy. And another way to say this is to say that force is equivalent to energy per unit distance. So in a vehicle, there's aerodynamic drag and friction drag, which are normally measured in units of force, such as pounds, and this can be converted by the equivalency of 1 pound is the same as 2 watt-hours per mile. So for every pound of aerodynamic drag, the energy required is 2 watt-hours per mile. For other losses or loads in the car, we can convert that by simply taking the power and divided by the speed, and we'll come up with units of watt-hours per mile. So if we add all of these numbers of watt-hours per mile, that gives us the total energy required by the vehicle for traveling. This is a summary of that energy budget for the van traveling at a steady 55 miles an hour. The aerodynamic drag is about 75 pounds, which is equivalent to 150 watt-hours per mile. The friction drag is similar. The system losses amount to about 70 watt-hours per mile. And other electrical loads, we can say, range anywhere from 0 to 100 watt-hours per mile, depending on how many things are turned on, such as heating or air conditioning, lights, etc. So that gives us a total energy consumption for this vehicle of between 360 and 460 watt-hours per mile. If we have a 40 kilowatt hour battery, that means that the range is between 87 and 110 miles. The 110 mile range was demonstrated with a road test. With an 80% depth of discharge, this comes out to between 70 and 90 miles. And it turns out that with a range of 60 miles, that will accommodate 90% of the users for 80% of the days in a year for 80% of the miles traveled in a year. But it's always good to have the range be increased. With a 100 kilowatt hour battery, the energy and the range will be increased by a factor of 2.5. Some vehicle road tests were done using this general approach. The vehicles were equipped with a data logger which recorded the speed, time, voltage, and current. The vehicles were put through a coast down test, and that type of test is used to determine the aerodynamic drag and the friction drag. After that data was collected, the performance analysis determined the speed versus time relationship, the acceleration versus time, thrust versus speed to overcome drag and accelerate the vehicle, and from this we can determine the motor power and torque versus RPM with a simple road test, rather than taking the motor out of the vehicle and putting it on a dynamometer. We can also gather overall system efficiency, which is the motor power over battery power, and over most conditions this amounted to about 88%. This is a road test that was done on the van back in March when it weighed 5,900 pounds. This was with 2 people in the van. The vehicle was accelerated to 75 miles an hour under maximum power and then slowed back to rest using maximum regenerative braking. It took about 30 seconds to get to 75 miles an hour and then about 11 seconds to get back down to rest. The acceleration shown in the green curve started out at about 0.3 of a G, and that tapered off to nearly 0. And then on the regenerative braking side, the deceleration was about 0.4 of a G. When we can convert this back into the power output and torque output of the motor, and during this test the motor RPM went from 0 up to 10,000 and back to 0 again. The positive part of the curve has to do with accelerating, and the negative part has to do with decelerating. The horsepower went up to 100 horsepower, stayed constant through most of the time, and then went negative to about 275 horsepower. And the torque, as you can see, started out roughly 200 foot-pounds and went to a maximum of 250 foot-pounds. Both the torque and the power came to 0 at about 7 miles an hour, which means that there's no more regenerative braking at that point, and the friction brakes have to be used. The Dodge Dakota pickup truck was also road tested, and this particular vehicle is available from the factory with several different sizes of internal combustion engines, ranging from 125 horsepower up to 230 horsepower. The vehicle equipped with a 100 horsepower electric motor performed midway between the 125 and 170 horsepower internal combustion engine. These are supposed to represent acceleration curves. They're not really straight lines, but the point of interest is the amount of time to get to 60 miles an hour. So the 125 horsepower V6 version took 14 seconds, and the Westinghouse powered vehicle took about 12.5 seconds. So the reason that less horsepower in the electric motor does better than the internal combustion engine can be explained by looking at the total vehicle weight or inertia of these two vehicles. The bar chart on the left itemizes the weight that is made up, or that constitutes the electric vehicle. The 3 bars on the right indicate the weight of a similar internal combustion engine vehicle, and the overall inertia depends on what gear ratio that vehicle is in. So we can see on the left that the battery weight, shown in green, is substantial for the electric vehicle and is minimal for the other vehicle. The drivetrain weight is about the same. The chassis and passengers is the same in either case, but the big difference has to do with the rotational inertia of either the motor or the internal combustion engine. In the case of the electric motor, the rotor adds about 4% to the total vehicle inertia. But with the piston engine vehicle, the inertia is much greater, and its effect varies with the square of the gear ratio, so that in low gear ratios, the effect of the motor can almost double the total vehicle inertia. So here's another example that shows a hypothetical contest between an internal combustion engine vehicle that can produce 150 horsepower and an electric vehicle that produces 100 horsepower. The yellow curve and the red curve should be the same color. The yellow curve indicates the horsepower that's actually delivered as a function of time, and the red curve indicates the average horsepower over time. That compared with the electric motor, the straight line shows the actual power delivered, and the curved line in blue below it indicates the average power. So even though the internal combustion engine has a higher power, the average power delivered by the electric vehicle is greater during acceleration. In fact, it works out that a 100 horsepower electric motor is equivalent to about 142 horsepower internal combustion engine as far as acceleration is concerned, from 0 to 60 miles an hour. This last chart shows a summary of the near-term and far-term parameters for electric vehicles, and most of these have to do with the battery. The near-term parameters have to do with the nickel-iron battery technology, and the far-term parameters have to do with higher energy density batteries that you'll hear about later on this morning. Going to a higher battery density will either increase the range or reduce the weight, or some combination of both. By increasing the voltage, we can decrease the current and increase the system efficiency and lower the cost of the power electronics. The present motor power of 100 horsepower is probably sufficient for near-term and far-term electric vehicle needs. That concludes my presentation. Are there any questions?
We don't want to comment on the first one at all.
Okay.
I have a comment which I think may reflect to all of you. The units, either we use metric system or use English system, or we use both. What I've seen here is a complete mix, American American English, the way wherever you want to, you use metric system, otherwise you use English system. In this particular environment of presentation, we'll have EC visitors. I think it would be nice for their easy understanding to have either metric system or both rather than a mix.
Is it all right to use both horsepower and watts?
Yes, but both in complete way.
You're saying always show the metric as well as the
Yes.
American. I consider.
That's really American, because English is now using metric system. For instance, people are talking about
Kilometers per hour.
40 kilowatt driving shaft horsepower.
Mm-hmm.
Shaft, I just did it.
Output power.
Output power. And then we talk about equivalent to 50 horsepower.
Well, we have found in our discussions with Chrysler that they are thoroughly tuned into horsepower and foot-pounds.
Chrysler, Ford, and General Motors understand you perfectly, but they're not going to be the only people. Ted Lester was in the International Electric Vehicles Symposium. There, everybody's talking about metrics. And if we're going to market this overseas, we have overseas visitors in the audience. I just want to suggest all of the electric vehicle people, if it's not too late, be consistent with one system and parenthesis with the international system. Just for your information, I believe the United States code for acquisition is such that beginning January 1, 1993, all acquisitions will be specified in metric system by the government. Now, for chemistry, battery people, it's very easy. This is always metrics. Physicists is always. It's the engineer, especially in the motor and generator engineers.
Well-
I would suggest very strongly that somehow a consistency is there.
Should
All
the,
the slides get changed.
should we change the slides to show both?
Yeah, that's what he's saying.
Yeah.
I mean,
Or you can add another one just to summarize in metric. But, you know, I was very sensitive to that because I just went through 4 days listening to metrics. And when the Americans come in, you pull up these computers and well, what is the conversion? 746 watts equal to 1 horsepower, or approximately 750. The conversion, you lose your audience. Or you might want to, if you really want to save money, save time, put a conversion table someplace.
Well, in each place where it mentioned pounds, we could put kilograms in parentheses, or the other way around?
Because the battery, for instance, especially later on you're going to talk about battery. The spec of battery has always been in the international forum.
Okay, if we convert the slides,
Kilowatt-hour per kilograms.
if we indicate both pounds and kilograms, for example, should we have the kilograms in parentheses or the pounds in parentheses?
Hard choice.
Doesn't matter, your choice.
But I mean, they should all of the whole presentation should be the same.
Everywhere,
Be
make sure you
consistent.
show both, you know, be consistent, but that one of them is always in parentheses. But
Okay.
miles per hour, put kilometers.
Okay.
You have 15 minutes to deliver your substance. You don't want them to spend 10 minutes to do the conversion.
Okay.
That would be my suggestion. About the battery people, do they have the same problem? Probably not, because batteries and chemistry people are always the electric system.
I don't know, we'll find out.
Okay. Thanks. It was
Okay.
good. I mean, John?
Well, I was so mesmerized by the subject, I forgot I was here as a critic, which I think is a positive. I think I'd like to see another last slide of something more.
More of a summary, a better summary?
Positive of what, these are just numbers and it leaves me cold just looking at the statistic number in the last slide, that's all.
Well, I guess what I was trying to get across, and maybe it didn't come across very well, is that the system that we developed is very good based on what batteries are available right now. And as time moves on, batteries will improve, and batteries has always been the stone around everyone's neck as far as electric
Well,
vehicles.
I don't take any issue with that chart, but I think a statement like that at the end,
Okay.
we've got this one and we're working towards the future.
By the time Ted comes back, you will know. In this whole wide world, nobody has developed electric private train of that power level. Mostly 40 kilowatt. In fact, I don't want to mention the word horsepower.
I gotta convert that.
The whole world's activities. And we have the highest horsepower, smooth operation capability.
There's one thing that might be, would have helped me, and I don't, is this 275 horsepower braking
Mm-hmm.
leaves me cold. I don't, I want to brake in a hurry. How much of a hurry does that brake in?
Well, the acceleration showed 0.4 of a G, and I was driving it at the time, and it was quite a bit of braking. The reason the horsepower is so much higher is because of the voltage is higher. Voltage goes up to 300 volts, and so.
Yeah, but if I'm in there and I want to brake, does
Well, see
that stop me and
Compare it to what you're saying.
just
do some-
compare it to something?
Compare it to what it is in an IC engine. You say something to the effect that you
Well-
break as fast, if not faster, than an IC.
Well, see, the vehicle would be equipped with both kinds of braking and just one brake pedal. So that when you first step on the pedal, the motor absorbs the energy, and if that's not enough, you can press on it harder and stop as fast as you possibly can.
Was 275 horsepower braking almost brake the wheels as quick as if I slammed on brakes?
Well, no, it's 0.4 of a G, and if you slam on the brakes, you can get close to 1 G.
Oh, okay, well, that would help.
How about
Okay.
another way? You did announce that you can do from 0 to 60 miles per hour within 12.5 seconds.
That's right.
Now, suppose you are running at 60 miles an hour using this particular brake system. What's the length of time it will take to stop?
The automotive tests show how many feet it takes you to stop at a certain mile per hour. That was it.
Well,
20 feet.
I just think you ought to think about it. 275 horsepower doesn't mean anything to me. Anyway.
okay.
It might mean a lot to a lot of other people, but it doesn't mean anything.
Yeah, we can't resolve it here, we need to move on.
Okay.
We'll take this down.
Let me run these in a hurry. There are a couple of typographical errors on the electrical vehicle development overview. There's a word consumption, some other word. It's not consumption, it's something else. On the electric motor deliver, it says, you mean to say delivers, and the title says deliveries. Other than that, what I've heard other people say, comparisons with real-life cars, I think, are interesting. The most interesting visual you showed me was the Dakota curve that showed that you actually outperformed one of the motors, the engines that's available on the market. I agree with John Walker when he said the ending seems a little abrupt. Even though the title of the slide says summary, it needs to be more rousing.
Okay.
Possibly, what you could do would be to, there are a lot of things you could do, but you could close out with 2 magazine covers that Tech Hubs could make for you, one from Road and Track and one from Car and Driver, where they take their cover and fake our electric vehicle on the covers of those 2 books. Now, you'd have to acknowledge that we put those together, but you could do something like that, or you could take a 2-page spread ad for Chrysler minivans and dummy it up with our electric vehicle in those ads. Something to get you off, but I think in general the ending should be more rousing.
Okay.
In the question and answer thing we had here afterwards, one of the things that struck me was you brought out your own personal experience. I was driving this vehicle. You know, maybe there's a way to work that in a little bit.
Excuse me, what was the other typographical error? Energy consumption was one, and what was the other one?
Consumption on the overview,
Uh-huh.
there's some other word there that's just the wrong word.
Right.
And on the electric motor, it says deliveries instead of deliveries. I'm pretty sure you mean deliveries.
We've got a lot of very good material in this, and I agree with other people are saying. One thing that struck me, that there was one curve that I had a tough time following. I think it's this horsepower torque curve where you went across the top of it and then
Right.
you double back. I think I'm always referencing, if I see a plot up there going from left to right, not
Well,
right to left.
yeah, I understand that confusion, and that's why I mentioned that during that test, the motor speed went from 0 to 10,000 and back to 0. So there was no time line on that curve anywhere.
Could you, one way might be to flip the bottom part over to the right, so it's a left to right continuum, yet you're plotting the differences of what the motor's doing.
Frank, what's this community used to seeing? They're used to seeing it go back to 0? People that
I don't know. I think that's the only way you can really express it, because we're talking, in one case it's positive, in one case it's negative, and those positive and negative values exist at a certain speed. And I think if I spend a little bit more time explaining what that chart is, that as far as time is concerned, it goes across the top and then comes across the bottom, and that in one case it's delivering, in one case it's absorbing.
If you're boxed in, maybe you could do a progressive disclosure and only show the upper half and discuss it, and then when you show the lower half, block off the top one.
Okay.
If I made it absolute talk, I could hit it all on the top, right?
Pardon me?
If I made it absolute value, it could be all across positive and go continuum.
As an old motor generator guy, I understand what you're talking about. there isn't. But I think the most audience are not familiar with regenerative braking, so a little bit tutorial.
Okay.
Would help.
Sure.
The back?
Yeah, one of the points when your car was better than the Dodge Dakota, you said we were between. Why don't you say we're better? Show where we're the best.
Okay.
Better.
Okay.
Below us. And I agree, some of the graphs, I had a hard time understanding. After studying them, I understood them, but at that time I wasn't listening to you.
Okay.
Barbara?
Frank, I thought you did very well. You did great on time, and I think the pace was really good. I agree. I thought the ending was weak, but you were so confident all the way through, and the ending kind of left.
Mhm.
And you-
Yeah, I knew that would happen.
And you also need to when you do it, introduce the fact that you're going to hear. Maybe Ted's going to do that up front. You're going to hear, that you're covering the system, and then you're going to hear more specifics about the motor, the controller, and the battery later in the session.
It was unclear if Ted would talk about that or I would,
Okay.
but
Well, you guys
I think
need to do
Ted will do that.
Well, you don't have to be obnoxious about it, but I think you ought to brag a little bit.
Mike?
I thought this was a great tutorial, but I'm not sure what Westinghouse does.
Well, this sort of lays the groundwork for the next three presentations, which are going to go into more detail. One is on the motor, one is on the motor controller, and one is on the battery. And this just kind of, like you say, gives a tutorial so that people understand what the next three presentations are about. I think that was the purpose of this presentation.
Oh, that was the purpose, you did your job. Good.
Okay. Yes.
I kind of had the same feeling. I saw a lot of this and I thought, well, so what? Maybe you could reference the future presentations.
Okay.
That you'll see more of this when so-and-so talks.
Well, when the block